The texture of spacetime is shifting so rapidly that it's alarming. Our night sky is undergoing significant changes, and in just a few years, if not sooner, it could become entirely unrecognizable. Astronomers around the world are sounding the alarm, and experts like Neil deGrasse Tyson have recently confirmed the impending explosion of Polaris. The story surrounding this phenomenon is quite unsettling. Polaris, also known as the North Star, has long been a stable presence in our night sky, serving as a crucial reference point for astronomers, navigators, and explorers. However, this stability may soon be disrupted. In September 2023, a paper presented by the esteemed Royal Astronomical Society raised concerns about the fate of this celestial beacon, suggesting that Polaris is nearing its explosive end and could soon vanish from the night sky. Before diving into the implications of this discovery, let's learn more about Polaris. Located nearly directly above Earth's North Pole, it appears almost fixed in the northern sky. Found in the constellation Ursa Minor, Polaris is a bright yellow-white supergiant star, significantly larger and brighter than our Sun. It is not a solitary star. Rather, it is part of a complex triple star system, with Polaris A and Polaris B forming a binary pair, while Polaris AB orbits around them. The gravitational interactions between these stars shape their orbits and influence their behavior. Any disturbances in these interactions can lead to unpredictable variations in the star's brightness and pulsation patterns, although the specific dynamics behind these interactions remain unclear. Polaris is situated approximately 323 light-years away from Earth, meaning the light we observe from it today began its journey more than 300 years ago. Therefore, if Polaris were to explode, we wouldn't see it until over 3 centuries later. It's even possible that it has already detonated, and we are simply yet to witness the light from that event. Throughout history, the North Star has held immense cultural, navigational, and symbolic significance. Its steady position has made it an invaluable guide for ancient navigators traversing oceans and landscapes. Symbolically, Polaris represents constancy and direction, remaining unwavering amidst the ever-changing night sky. For astronomers, Polaris has been a critical reference point in studying celestial movements. As a Cepheid variable star, its periodic changes in brightness have provided vital insights into astronomical properties and the nature of variable stars. This characteristic has also played a crucial role in determining astronomical distances and calibrating instruments. Its pulsation follows a predictable pattern, allowing astronomers to anticipate its behavior. Recently, however, Polaris has deviated from this consistent behavior. This anomaly in its pulsation cycle has puzzled astronomers, leading to a closer examination of this celestial irregularity. Instead of its usual predictable pattern, Polaris has begun to exhibit erratic cycles of dimming and brightening. Researchers are increasingly concerned that the star may be approaching the end of its life, aligning with behaviors typically observed in stars nearing their demise. Notably, Polaris's pulsation period has been lengthening, which was previously stable. This change corresponds to an annual increase of about 4.5 seconds in its pulsation period. While this may seem minor, it has significant implications. Some astronomers speculate that gravitational interactions within the Polaris system could be causing these variations in its atmospheric conditions, directly affecting its pulsation patterns. Others express greater concern, believing that the star is on the brink of exploding. The similarities between Polaris's behavior and that of Betelgeuse, another well-known star in the Orion constellation, are striking. Both stars have exhibited perplexing anomalies in their brightness, raising alarms about potential explosions. Stars in their late stages of life often display such irregularities before reaching the pinnacle of their life cycles. While NASA has voiced heightened concern regarding Betelgeuse, Polaris has not yet received similar official scrutiny. As a Cepheid star approaches the end of its life, it undergoes several stages, including the main sequence stage, the red giant phase, and ultimately a supernova explosion. Based on the erratic behavior of Polaris, scientists predict it has entered the helium-burning phase, common among Cepheid stars nearing their end. However, definitive signs of its imminent explosion remain uncertain. Astrophysicists are diligently investigating these irregularities to comprehend Polaris's fate. Should Polaris explode, it would likely be a spectacular event in our sky, potentially outshining the moon and becoming one of the brightest objects visible for weeks or even months. Its appearance could dramatically alter our perception of neighboring celestial bodies like Ursa Major or Ursa Minor, of which Polaris is a part. Rest assured, Earth would probably remain completely safe, even in the event of a Polaris explosion, given its mass and distance from us. While a Polaris explosion may not be visually as stunning as that of Betelgeuse, it could still be visible to the naked eye for an extended period, dominating the nearby stars. Astronomers and observatories would undoubtedly take notice, sparking interest within the academic community and among stargazers worldwide. However, the specific visibility and impact on Earth's environment or atmospheric conditions would be less significant compared to a closer supernova event. What about Polaris itself? What lies ahead for it after a potential explosion? It's important to clarify that while massive stars typically end their lives with a supernova, this is unlikely to be the case for Polaris. When a massive star goes supernova, a colossal explosion occurs, marking the final destructive stage of its life. This process involves a complete collapse of the core, triggering a violent shockwave that causes the star to explode. However, Polaris is not massive enough to undergo such an explosion. Instead, as it exhausts its nuclear fuel, it will shed its outer layers and transform into a white dwarf. This transition will not result in a supernova but rather a gradual fading into a more stable state. A peaceful conclusion leads to a white dwarf, a dense remnant of a low or medium mass star that has exhausted its nuclear fuel. This white dwarf is astonishingly compact, comparable in mass to the Sun but compressed to the size of Earth. Once this occurs, we can no longer observe its remnants as we do with stars today. Analyzing the expected effects of Polaris's potential explosion against real cosmic events provides valuable insights into stellar evolution and their ultimate fates. Contrasting our expectations with observed supernovae like SN 1054 and SN 1987A, as well as later events such as SN 2011F and SN 2014J, yields crucial information about the likely consequences of Polaris's explosion. For instance, SN 1054 resulted in the formation of the Crab Nebula, which continues to expand and emit radiation across various frequencies, creating a rich field for astronomers to study. Similarly, SN 1987A, observed in the Large Magellanic Cloud, has offered insights into nucleosynthesis processes and the properties of supernova remnants. The formation of nebulae like the Crab Nebula occurs due to the ejection of material during the supernova explosion, which interacts with surrounding interstellar gas and dust, enriching it with heavy elements and contributing to the cycle of cosmic birth and death. Moreover, the release of cosmic rays and high-energy particles accelerated by supernova shockwaves has implications for astrophysical processes and cosmic radiation conditions. To make definitive comparisons, researchers assess differences in mass, structure, and velocity of ejected materials between the anticipated explosion of Polaris and other observed events. This involves studying light curves, spectra, and remnants from these occurrences, projecting similar characteristics for Polaris's potential explosion and evaluating whether it could lead to the formation of nebulae or distinct cosmic distributions. Another crucial area of investigation focuses on the pulsational variability of stars nearing their end stages, like Polaris, in comparison to observed supernova progenitors. This comparative analysis can help identify similarities or deviations, offering insights into the explosion mechanisms. Pulsational variability in stars at the end of their lives may signal internal instabilities or impending catastrophic events, providing clues to the evolutionary cycles that lead to supernova explosions. Despite meticulous observations and extensive research, astronomers are often perplexed by the anomalies observed in Polaris's behavior. Understanding the unique circumstances behind these anomalies is key to advancing our knowledge of stellar evolution. Grasping the mechanisms responsible for Polaris's irregular pulsations requires interdisciplinary collaboration and the development of advanced theoretical models and observational techniques. The potential loss of Polaris as a crucial reference point in the night sky raises significant concerns for astronomical endeavors. Ground-based telescopes and celestial measurements would need recalibration, affecting the precision of cosmic evaluations. The absence of Polaris could also disrupt navigation systems and cultural practices reliant on celestial landmarks, underscoring the significance of this astronomical event. The complex behavior exhibited by Polaris emphasizes the need for deeper investigations and dedicated research efforts. Astronomers must grapple with the intricacies surrounding its unpredictable pulsations and present concrete answers. Recognizing the importance of enhancing our understanding of celestial phenomena, the quest for knowledge about Polaris's fate remains uncertain, with time being the only revealer of its true nature. Regardless, the pursuit of knowledge and understanding, even amidst cosmic uncertainties, reflects humanity's enduring curiosity about unraveling the mysteries of the universe. As astronomers continue to monitor Polaris, the star's unusual behavior prompts a broader examination of similar celestial phenomena. Studying other variable stars, particularly those showing signs of irregular pulsations or unusual dimming and brightening cycles, is vital. By analyzing these stars, researchers can gain insights into the mechanisms driving such anomalies and their potential consequences. Observations of these stars will refine models of stellar evolution and lead to more accurate predictions about the life cycles of stars like Polaris. Additionally, advancements in technology and observational techniques play a crucial role in these studies. The development of more sensitive telescopes and space-based observatories allows for precise measurements of stellar brightness and pulsation patterns, enabling astronomers to detect subtle changes in stars that were previously undetectable, thereby enhancing our understanding of their behavior and potential fates. Another perspective under scrutiny is the role of interstellar conditions in shaping the behavior of stars approaching the end of their life cycles. The interaction between a star's material outflow and the surrounding interstellar medium can influence its observed properties. Studying these interactions helps researchers comprehend how a star's environment could affect its evolution and potential transition into a white dwarf or supernova. Furthermore, the impact of a potential Polaris explosion on other celestial bodies and cosmic phenomena is an area of interest. The shock waves and material ejected from such an event could influence nearby stars, planetary systems, and even the formation of new celestial objects. Understanding these potential effects provides a more comprehensive view of the astronomical cycles at play and highlights the interconnectedness of various cosmic events. The academic community remains committed to unraveling the mysteries surrounding Polaris and other celestial phenomena. Collaborative efforts across institutions and disciplines are essential for advancing our knowledge of the universe. The quest for answers regarding Polaris's fate and the broader implications of its behavior underscores the importance of ongoing research and the mission to understand the dynamic and ever-changing universe. In addition to focusing on individual stars like Polaris, scientists are also working to improve theoretical models that describe the life cycles of massive and variable stars. These models integrate data from a range of observational sources, including ground-based telescopes, space observatories, and laboratory simulations of cosmic conditions. The integration of diverse datasets helps refine our understanding of the processes governing stellar evolution, including the complex interactions within binary and multiple star systems. Astrophysicists are also investigating how supernova explosions might influence cosmic phenomena, such as galaxy formation and the distribution of heavy elements throughout the universe. Supernovae, including those from stars like Polaris, play a critical role in enriching the interstellar medium with elements essential for the formation of planets and life. By studying these events, researchers aim to gain insights into the life cycles of galaxies and the chemical evolution of the universe.